For nearly a century, astronomers have faced a cosmic contradiction. The universe behaves as if it contains far more matter than we can see. Galaxies spin too fast to hold themselves together, their stars bound by the gravitational grip of something invisible. This something is dark matter. It makes up about 85% of all matter in the universe, and yet we have never directly detected it. What is it made of? 1 mile beneath the Black Hills of South Dakota, in an ultra-clean lab shielded from cosmic rays, one of the most sensitive scientific instruments ever built is listening for the faintest whisper of this elusive substance. This is the story of the LUX-ZEPLIN experiment and how its latest findings are rewriting the rules in the epic quest to uncover dark matter's true identity. At its heart, LZ is a giant, high-tech trap. Its core is a 2-story tall, 7-ton vat of ultra-pure liquid xenon, so dense it creates a perfectly isolated environment. The principle is simple in theory. If a dark matter particle, known as a WIMP, passes through and bumps into a xenon atom, it should produce a tiny flash of light and free some electrons. These signals are the telltale signature LZ is built to capture with incredible precision. But the universe is a noisy place. To hear this cosmic whisper, LZ had to be built to be silent. It's shielded a mile underground from cosmic rays, constructed from thousands of ultra-clean, low-radiation parts and wrapped, like an onion, in layers of protection. A key layer is the outer detector, a huge tank of a special liquid that surrounds the xenon. Its job is to catch imposters.
The tricky thing about neutrons is that they also interact with the xenon nuclei, giving off a signal identical to what we expect from WIMPs. The outer detector is excellent at detecting neutrons and confirms a WIMP detection by not having any response.
In July 2025, the LZ collaboration released its most precise results yet. After analyzing a record 4.2 ton years of data, nearly 5 times more exposure than the previous world's best, the outcome is profound, yet silent. They did not find WIMPs, but in science, a null result is not a failure. It's a process of elimination. By not finding a signal, LZ has dramatically narrowed the possibilities for what dark matter could be, ruling out entire classes of theoretical particles and pushing into realms of weaker interaction than have ever been probed before. As physicist Hugh Lippincott of UC Santa Barbara puts it,
while we always hope to discover a new particle, it is important for particle physics that we are able to set bounds on what the dark matter might actually be.
This requires an extraordinary level of vigilance. The team must guard against subtle mimics, like the radioactive decay of radon, and even against their own unconscious biases.
We're pushing the boundary into a regime where people have not looked for dark matter before. There's a human tendency to want to see patterns in data, so it's really important that no bias wanders in. If you make a discovery, you want to get it right.
To ensure objectivity, they use a clever technique called salting, hiding the real data with fake signals until the very end of the analysis. It's a meticulous process, all to ensure that if a discovery is made, the world can believe it. LZ is not a machine run in isolation. It's the work of a vibrant international collaboration of about 250 scientists from over 36 institutions across the US, UK, Portugal, Switzerland, South Korea, and Australia. Much of the day-to-day work is driven by early career researchers, postdocs and graduate students who are the lifeblood of the experiment, and the search is broadening. While LZ hunts for WIMPs, other experiments are pursuing different candidates. Projects like DAMI-M, buried under the French Alps, are searching for much lighter, wimpier particles. Others are looking for hypothetical particles called axions by studying light from distant black holes as it passes through galaxy clusters. The hunt is happening on multiple fronts.
Our experiment is also sensitive to rare events with roots in diverse areas of physics. Some examples are solar neutrinos, the fascinating decays of certain xenon isotopes, and even other types of dark matter.
So, what's next? The LZ detector is still running. The plan is to collect data through 2028, aiming for a total of 1,000 days of exposure. With more data, the net will tighten even further. But the vision extends far beyond LZ. The leading xenon researchers from the LZ and Xenon collaborations have already joined forces to design a next-generation observatory. This future detector, with a multi-ton scale xenon target, aims to be at least 10 times more sensitive, poised for a definitive discovery. The journey to identify dark matter is a long game, a testament to human curiosity and perseverance. Each result, even one that doesn't find a signal, is a critical step forward. It eliminates possibilities, refines our theories, and sharpens our tools. The LZ experiment has not yet heard the whisper of dark matter, but it has made the room infinitely quieter, allowing us to listen more closely than ever before. In the profound silence deep underground, we are slowly, methodically, closing in on one of the universe's oldest and best-kept secrets. This video was based on the latest research from the LZ collaboration, published in Physical Review Letters in 2025.